Okay, good morning, everybody. Back to Math 152, Section 4, Lesson Analysis class. I am your SI Jeff Pork, and today I will be introducing you to sequences and series. Now, sequences and series can get a little tricky. They're a lot like integrals, but the notation and what they represent is usually confusing to students. So for this session, we're just going to focus on the basics. Starting with a sequence, which is basically a list of terms. All it is. We're going to take this example. We're going to be given a sequence, and we want to find the nth. So the point of this is basically to take a given sequence, which we could be given instead of a typical notation. We could be given a list of numbers, and we would just want to take that and convert it into basically a format that we can use to solve problems. So say we're given the sequence 1, negative 1/3, positive 1/9, negative 1/27th, and positive 1/81, continued on forever. I've given these terms. Assuming the sequence follows the same pattern, all we have to do is identify it. So we start at 1, and then reach negative 1/3, positive 1/9. So we can see here that each subsequent term is multiplied by negative 1/3. Now, remember that these terms are A1, A2, A3, A4, and we want to find A7. So we start with the integer 1, not 0, which means when we find our A7, we know that this is going to be 1/3 raised to some power n. Now you might think, okay, n, that's sufficient, right? We have, well, okay. Now, you might think n is sufficient, but unfortunately, because we start at a sub 1, negative 1/3 to the first is negative 1/3, not 1, which means in order to make this 1, we have to raise it to the 0 power. So we actually start our sequence at n minus 1. This is a common thing we'll have to account for. Basically, don't forget that we start at n equal to 1, and if we need n equal to 0, then we're going to have to subtract 1 from it. Okay, so pretty straightforward stuff. Let's try another one. Let's say we have the sequence 5, 8, 11, 14, 17, 20, 23, 26, 29, this goes on and on. Okay. So we can clearly tell that from 5 to 8, add 3. 8 to 11, add 3. 11 to 14, add 3. Okay, so we're just adding 3 to our previous value, right? Now, trick here is we can't just say plus 3 because we're starting at 5 here. So when we write our nth term, a sub n, we're going to use our starting value 5, and then we're going to add 3 times n minus 1. Why times n minus 1? Well, because our first term is 5, which means we need to multiply by 0 in order to get rid of that 3. So as you can see, it's pretty straightforward. Just look for the pattern. Once you've identified the pattern, you've got to convert it into this end format. But basically create an equation that represents all the integer values of your sequence. Okay, so now we're going to do some basic convergence divergence. We want to determine whether A sub n converges or diverges. And say for this particular example, we have A sub n equal to n to the third over n to the third plus 1. Now, we're not 100% certain how to do something like this, but let's say we take a look at this and we create a function that represents the same values as our sequence at all the integer values of x. So let's say we take f of x and we set it equal to x to the third over x to the third plus 1. Now, because all these values are essentially the same, the exception of the fact that we can't have decimal values in our sequence, these are basically equivalent. So, in order to determine the convergence divergence of this sequence, all we have to do is determine whether this function converges or diverges. That's a theorem, can't quite remember the number, but sequence limits from function limits, essentially. So we will take the limit as x approaches infinity of x to the third over x to the third plus 1. Now we know that this is going to give us the indeterminate form infinity over infinity plus 1 if you like. So we just LH it, we tau. We get 3x squared over 3x squared. Nice and simple. Terms cancel one another, and we're just left with 1. So the sequence converges to this. The function converges to 1, which means our sequence converges to 1. So A sub n converges. By sequence limits from function limits. Okay. Let's take a look at another one. Say we have A sub n equal to -1 raised to the n over 2 root n. Okay. So, yet again, we're going to have to create a function that represents generally what we're looking at. Now, it should be noted, we have a -1 to the n, which means our function or our series is going to do something like this. Now, is that significant? It depends. When referring to series, generally speaking, we can liken the absolute value of A sub n to A sub n when we're talking about convergence divergence. So in this case, we're going to do the same thing as the last one. Just set up a function f of x equal equal to 1 over 2 root x. Take the limit as x approaches infinity. One over 2 root x, which is 0. You can tell that just by looking at it. The numerator is never going to change. The denominator keeps getting bigger. So we're going to keep getting closer and closer. Value 0. And if we look at the negative 1 to the n, regardless of whether that is factored in or not, we're approaching 0, which makes sense with what we thought this was going to look like. We said it was going to be something along the lines of this. So in terms of whether the sequence can be the negative actually isn't going to make a difference. So from this limit, we know that a sub n, a sub n A sub n converges. Excuse me. Now, on to our next step. All right. So now we're going to be talking about series. Now, what is a series? A series is a sum of a sequence. Just take your, excuse me, all the sequence terms, sum them up. So this is going to be denoted in form in what we call sigma notation. In this case, it's going to be n equals to 0 up to infinity of pi to the n over 3 to the n plus 1. So this is the sum of all terms in the sequence pi to the n over 3 to the n plus 1. All right. So let's say we want to determine convergence divergence. Okay. Now, this one can be a little tricky. In this case, we can figure it out with a little bit of intuition and recognition. Now, if we look at the first some odd terms of this sequence, we're going to have 1/3 plus pi over 9 plus pi squared over 27 plus 9. Now, we can very clearly see there's a common multiplier between the terms of these sequences, between the terms of this series. And that multiplier, we'll call it, I think it's R, common ratio, R, is equal to pi over 3. So 1/3 multiplied by pi over 3, we get pi over 9. Multiply that by pi over 3, we get pi squared over 27. So when we have this common ratio, we have what's called a geometric series. If you can find a common ratio, you have a geometric series, and that is going to make your life a whole lot easier. Because if you look in the book, there are very simple rules for whether a geometric series converges or diverges. In this case, R is equal to pi over 3 is greater than 1. And because it's greater than 1, then that means this geometric series diverges. Alright, I think we'll have one more today. Problem number 6. Same thing, convergence, divergence, sigma, sequence, starting at k equals 0, going to infinity of pi over 3 raised to k. All right. So again, a good way to analyze these things, write out the first few terms. We have 1 pi over 3, pi squared over 9, pi to the third over 27, yada. Now these commas should be pluses. Just sort of used to write sequences, I guess. But yet again, we can see very clearly that there is a common ratio between these things. In this case, our common ratio is pi over 3. How about that? It's the exact same thing as the last one. Wow. Okay, so yet again, that's greater than 1. This series is divergent. I suppose we should probably do one more, given that that wasn't exactly. Sorry about that. Let's see here. Okay, so let's say now we have the sequence sigma n equals 1 to infinity of 1 over n raised to the 5th power. Now, right out the first couple of terms, we'll have 1 over 1 plus 1 over 2 to the 5th plus 1 over 3 to the 5th plus. There's no real common, so we know we don't have a geometric. We're going to have to try something else. Now, we look at 1 over n to the 5th and we say, well, that is basically the same. A sub n is equivalent to, say, f of x is equal to 1 over x to the 5th. Now, how does that help us? Well, we can take sequence limits from function limits, and we can apply that to this idea of series. Now, in this case, we're actually going to take an integral. We'll say that the integral from 1 to infinity of 1 over x to the 5th dx. So this is an improper integral. We know what to do there. We take the limit as b approaches infinity, integral from 1 to b of 1 over x to the 5th dx, which I believe comes out to limit b approaches infinity. Let's see here, we have negative 1 over 4x to the 4th. And we evaluate this from 1 to b. So we'll have the limit as b goes to infinity of negative 1 over 4b to the 4th minus negative 1 over 4 times 1 to the 4th This becomes plus positive. This term approaches 0. This term is 1/4. Which means our limit is equal to 1/4. So, limit exists, which means the excuse me, series converges. So, because this limit exists, the series converges by what we call integral test. Okay, so there you have it. Basic intro to what we'll be dealing with over the next couple of weeks. Hope that was helpful. Have any questions, feel free to ask. And that's a wrap.